everyone. My name is Mark Sokol. I am the Chief Technology Officer of Falcon Space. This is a research startup. It says advancing anti-gravity technology, but we did change that to advanced propulsion research and development. Basically, we're looking at ways to travel through space without expelling anything in the other direction. And there's lots of theories and ideas out there. We're the people who actually put those ideas to the test. We're located in Hawthorne, New Jersey. There's another company located in another Hawthorne. We're not going to mention them. Falcon, that's actually my last name, Sokol, so it means falcon in Russian. Okay, so the problem with space travel. Science says that faster than light space travel is basically impossible, and there's two reasons for that. Relativity, we have E equals mc squared, the energy and mass equivalency principle. And then we also have the rocket equation. That's the delta V, the velocity that you're going to move in one way is equal to the amount of mass you throw out the other way divided by the amount of mass that you want to go in the way that you want to go. What these two equations have in common is m, that little pesky thing, mass. So let's dive in on the problem and see where's mass come from. So the Higgs mechanism, otherwise known as the Higgs boson, accounts for less than 1%, or that's where the electrons get their energy. But most of the mass is coming from the strong nuclear binding energy. That's around 99% of it, and all the other energies that relativistic, kinetic, those things are negligible when compared to the strong nuclear force. So let's dive in on the strong nuclear force. What can we do to the strong nuclear force? There's an effect called dynamic nuclear polarization. It was discovered in the late 40s, maybe early 50s. It's connected to ESR, electron paramagnetic resonance, which is a subset of nuclear magnetic resonance. So basically, this is a little confusing. If during the Q&A, I could explain this a little deeper. But basically, electron Larmor precession, that's the precession of the electron spin, is energized in a laminar magnetic field using microwaves. And these energized electrons can then radiate their energy to the nucleus via the hyperfine coupling that orients subatomic particle spins. And the strong nuclear force, which is essentially the binding between protons and neutrons, accounts for 99% of the atomic mass, becomes aligned due to this coherent nuclear spin state. And spin orientation alters how the strong force interacts with the quantum vacuum along the plane and axis of spin. So we're kind of making a squeeze state of the strong force. And I'm using lots of technical jargon, but I could explain it deeper if we had more time. Basically, there's several theories as to why this would reduce the mass to the degree that DNP is achieved. And by reducing mass, you basically can either use a smaller rocket, or if you get it low enough, you can use other forms of propulsion to travel through space. Now, if you could get the mass down to 0, which would be pretty cool, technically could even time travel. So where did this idea come from? Well, I first heard about it from this guy named Frederick Alzafon, who published a patent on it back in the 80s. And this was based on his own research. The patent was denied on national security grounds, but at the same time, he did publish a paper because he already had a patent pending. The paper was accepted and was presented at the AIAA in 1981, Colorado Springs. And on the right over here, you see basically the experimental setup. It's pretty simple. You guys at Bell Labs should be familiar with some of these things: lock-in amplifiers, FM detectors, microwave source, and a homogeneous magnetic field. So this is something that we at Falcon Space attempted to try. This is our S-band version. The Klystron unfortunately did not have good enough vacuum, so this setup had to be shelved. It looks pretty cool, though. For a laminar magnetic field, we profiled the magnetic field using a laser and a B-field detector or Gauss meter, and made a graph out of it, and then used our machine shop to basically machine out what you'd call a magnetic lens that solved the inhomogeneity. This is just an example of the kind of ingenuity we use at Falcon Space in order to achieve these goals. This is our X-band setup inside the RF chamber, the Faraday cage. If anyone's played with X-band, it gives you a nasty headache. So we built a chamber to protect us from it. And this is the S-band setup, or 3 gigahertz. This can detect this effect at cryogenic temperatures at hard vacuum, like -7 torr. I was actually just came from working on it earlier today. And we have parts of it over here that were just picked up from Home Depot. But yeah, this is how the sample is stuck in there. We use the controller of I think it was SEM, a scanning electron microscope, to hold the sample test rig. But so experimental results. So this is from our X-band setup. This is a paper that I presented. I have copies of it over here if anyone wants. At the ENC, Experimental Nuclear Magnetic Resonance Conference back in Asilomar, California. And what you're looking at is the weight change over time over magnetic field sweep. So as we're sweeping through the magnetic field with a constant RF pulse, when the dynamic nuclear polarization is expected to happen, we see a massive dip. These are 3 runs that are overlaid on top of each other. So it gave us a high level of confidence that we're actually seeing a real effect. And the final post over here. So the next version of this, we're looking at keeping the magnetic field on board. And in doing so, we'd be able to couple to it directly and basically remove any doubt that we're seeing a real effect. To get involved, we have our website, falconspace.org. You can contact us if you'd like to invest, if you'd like to collaborate in some way, and hoping to hear from you guys.